go ahead and do WarmUp 9.4, and you may be finishing this back page, but I'm going to go up here and start here on the front. Okay. Because you have two logs over here on this one side, you have to condense them into a single log. And so to condense those, we know that since they are adding, then those inside terms will multiply. So we've got log base 7 of x plus 2 times x minus 2, and that's equaling log base 7 of 2x minus 1. Now that I have these a single log on both sides and they're the same, I can raise them to the power and get rid of the log base 7. So that leaves me with 2x minus 1 equaling x plus 2 times x minus 2, which I, of course, am going to FOIL that and then solve that quadratic. Okay, so now I have a quadratic. I'm going to move things around, and I'm skipping all this step here. So you can add your 1, subtract your 2x, and then factor. Those end up factoring as x minus 3 and x plus 1. So therefore, the solutions that I have are 3 and negative 1. Now, where was the variable located on this problem? In the log. So because the variable is located in the log, we have this type of picture happening, and therefore, tell me about my domain. Good. My domain, it also can't be 0. Can't be negative or 0. My domain is from 0 to infinity. So I have to take this 3 and put it up here in the log and make sure that all of those are what I need them to be. Was 3 good for all of those? Yes. What? What's inside the log, yes, has to be positive. And by doing 2 times 3 minus 1, that checks out. 3 plus 2 checks out. And 3 minus 2 checks out. So that's all good. But let's say I go through, as long as it's positive, right? Not 0 and not negative. Okay? Oh, well, I mean, you could go in there and you could actually calculate it. The question is how you know that 4 isn't the answer. I mean, you could go in there and you could actually calculate it. I mean, but we solved, and 4 wouldn't have worked because it wouldn't have factored correctly there. So, I mean, you could go back in there and you could actually physically check those numbers. But all I need to do is just make sure that it's not something out here that gives me an imaginary solution. Now, if I put this negative 1 in here, then what does that give me right here in this first term? That gives me negative. So this one ends up being extraneous. It's out here, and, you know, there's no graph out there. So negative 1 ended up being extraneous. Therefore, 3 is the only solution for number 1. Okay, number 2. There are actually a couple ways that you can solve this, and, you know, it's up to you to decide which way you like best. The one way is this, and this may not have been the way you had done this, but look at this. I think we sometimes miss seeing this. This log base 5 of 2 is an actual value. Okay? Sometimes we just rush to get all of our logs together, and then we miss the fact that that's an actual number, and so simplify it. So I'm going to do that. In fact, this isn't even the way I had done it on my notes, but I'm going to try doing this problem this way. So how do I calculate that value of log base 5 of 2? Remember, change of base formula. Log what? No, log 2. Remember, change of base formula says that this is log 2 divided by log 5. And I can find that actual value of that. Okay, so let's go back and do that. So log, yeah, I think that might be easier Then doing the other way, you know, I don't know. To each his own. So that's that value. So this is 1 minus 0.4, what was it, 0.4307 or something?
It's 4307.
Okay. Okay, and 1 minus that. Now don't forget that little technique in your calculator. You can go 1 minus second answer, and that will bring back the whole previous answer. And so that's 0.5693. Okay. This is another common place that we tend to get stuck. You have a single log. You have a single log. How do you handle just a single log and get rid of a single log? Correct. Put it back into exponential form. Okay. Rearrange it in exponential form. So I would be saying 5 to this power, you know, wild lovely. That's that power right there. So 5 to that 0.5693 power is 3x plus 1. You know, and if I wanted to be really, really accurate, then probably in my calculator, since I already have that entire decimal stored in, I'm going to go 5 to the, and how could I pull up that whole entire decimal? Second answer. So see, I'm being completely accurate, and I haven't lost anything in the rounding process. And that ends up being the very lovely 2.5 equals 3x plus 1. Now this is something totally normal. You can end up doing your regular old algebra 1, and I think that you get the answer is 1/2. Okay? So that's one way to do it. It may not have been the way that you did it. It actually is not the way I had done it on my notes. Would you like to see the other way? I mean, did somebody do it another way and you need to, I'll start it, but I won't finish it out. Okay, now don't forget, since our variable's in the log, do we need to check this? Yes. We need to put that half in right there and make sure that that's fine. And yeah, that's 1.5 plus 1, and so that's all good. It's within the domain, so it's a reasonable answer, therefore it's fine. Okay. But let me go ahead and show you the other way that I did this problem real quickly. Yeah. Okay, the way I had done this on my notes from last year is I added this log base 5 of 2 over. And so I have log base 5, 3x plus 1, plus log base 5 of 2 equaling 1. And now I can condense these logs together, and I get log base 5. This actually is looking pretty much easier. 6x plus 2. I went ahead and multiplied 2 times 3x plus 1 and did 2 steps at once and distributed, equaling 1. Oh yeah, I like this. It's easier. Then what happens? How do I get rid of a single log? No, don't log both sides. You write it as an exponent. If you only have a single log, you write it as an exponent. So 5 to the 1 equals 6x plus 2, and then you can solve it that way. Yeah, that I think actually ended up being easy. So it's to each his own, whichever way you liked. Here we go. Number 3, both of these variables are up there in the exponent, so how am I going to get those down? Log them. Okay. So I'm not going to go through this completely, except for that there is a common error I see happening, or a common place that I keep getting questions. People are getting stuck at this one particular point. And so I'm going to bring that x down. I'm going to bring those variables, those exponents down. Okay, here's where we get stuck. Or here's where I keep getting questions. What are you going to do? Okay, if I divide by log 2. I do like that. That's my preference. I prefer to get away from the parentheses that has 2 terms in it. I think that's the simplest way. So I'm going to divide by this log 2, and I'm divide by this log 2. And now, look at this. This is, again, where we get stuck. That's a number. Log 3 divided by log 2 is a number, and that acts as that is the coefficient to the x. So, see, here I have log 3 divided by log 2, and that's 1.585. That is my coefficient to this x term. 1.585x equals x plus 3. Now what? It's a regular Algebra 1 problem. It may look strange because you have decimals involved, but I would just subtract x, and then I would be dividing by 0.585. And I get the answer of 5.1282. Now, do I need to check that? Why do I not need to check it? Good, because the variables were in the exponents. And the domain of an exponential function is negative infinity to infinity. So that's all good. As long as it was real, it's fine. So I'm not going to do number 4. It follows the same. How do the x's not cancel? Okay, hold on. Okay, let me go back because we're getting some questions here. Apparently I zipped through this part right here. Let me pull this over. 1.585 x's equaling x plus 3. When I subtract this x, that's a 1x. I'm subtracting away, and that kind of looked bad there. I'm subtracting away a 1x. And so that's 1.585 minus 1, which is 0.585x equals 3. Now I divide by 0.585 on both sides. And that's how I got the answer, 5.1282, or whatever. I might have had a different answer than you. I could have been, I don't know, I may have done it in my calculator more accurately and left all the decimals in there, something like that. Okay? So I'm sorry, I didn't mean to zip through all of that, but that's what happens there. Can I skip 4 and just give you the answer there?
I did the other way. I divided by log 3 or something like that.
Correct, yes. That, you can do that. Okay, the answer, by the way, for number 4 ends up being 12.4224. Okay? Yeah, if you're off by a couple of thousandths or, 10 thousandths of decimals, that's fine. That's a rounding issue. Okay. Next. The back is actually the word problems like 8.4. Those ones that I did on the front were because we were having some continuing questions still on 9.3, and I needed to keep those skills going. So here are actually the questions. We're compounding interest, so we're going to be using this formula. What's N represent? N is the number of times it's compounded in a year. So here, it's compounded annually, so what is N? 1. 6% rate as a decimal. How long will it take for a principal to triple? Oh, interesting. How are you going to do that? We're tripling the principal. Yeah. So, my principal, 1 plus 0.06 divided by 1 to the 1t. And so what am I wanting the A to become? 3p. I don't know what that starting principal is, but I want it tripled. And so whatever it is, it's 3 times that amount. Okay? And then you just solve from there. What would you do? Divide by p's. So therefore, 3 equals 1.06 to the t. And what am I going to do now that my variable's in the exponent? Okay. Yes, the question is, can't you just go ahead and set up it as 3 and 1 here? Just put a 3 here and a 1 here and cancel the p's. Yes, you can just do that. But I went ahead and showed you that p there to show you exactly what happens to that p. Okay, so I'm logging both sides to pull those down. And so I'm not going to give you, I'm not going to finish that. That's a pretty basic log problem to do. And the answer there ends up being 18.854 something. Okay, so that would be how many years it would take your principal to triple. So that would be if you had an annual 6% interest rate. Not too bad. Okay, next. If the growth of the world's population is continuously increasing, so we do know continuous at a rate of 2%, how long will it take the world's population to double? Yes, I'm going to use the E model, and I'm wanting it to double. So A is my starting amount. What's my rate? 0.02t. What am I putting over here? I want it to be what? Double. So what do I put here for y? 2a. Because it started at a, and so doubling would be 2a. Yes, you can just do 1 and 2. I mean, it's fine. You can do 1 and 2, but I have to show you physically. I mean, a lot of you are saying, okay, you can just do 1 and 2. But I need to show you that it's not, you know, technically that is what's happening. That's why you're just doing 1 and 2. Okay, so we've got this. A stands for your starting amount. And so what am I going to do to solve this? Natural log both sides. So I'm going to natural log both sides. And tell me about natural log E. It's 1. And so then I'm just going to divide by 0.02 and get my answer. And T, that means the world's population would double in 34.6574 years. No, but do something like this here. Got it that way. Okay, next, number 7. In the city of Scranton, the number of game rentals is continuously increasing at a rate of 7.5% per year. For the last year that the data was available, 1.3 million games were rented. So that would be our starting. And what would it take us to get to 2 million? So what model am I going to use if it's continuously increasing? The E model. Okay, so I want to achieve 2 million. I'm just going to leave this in millions. It started at 1.3 e to the 0.075t, and then you're going to solve it from there. Questions on that solving? It ends up being 5.7441 years. Okay? All right, so that's the end of warm-up.